Test, audio. Audio test. Are we live? Where are you? Oopsie. Who's playing the music? I think this one's playing the music. All I need is you. Good morning, everyone. Happy whatever day it is, Tuesday. Hope you are rested and ready to go for another day of Chem 1. So last time we were talking about bond dissociation energies, and we often call them energies as the breaking of a single bond. We call them average bond enthalpies. I got overheads on. Do I have enough light? We call them bond enthalpies. We take the average of a lot of bonds, a lot of similar carbon-carbon bonds, carbon-carbon double bonds, carbon-hydrogen, hydrogen-oxygen bonds. We take those averages and we make a convenient table. The advantage of that is, compared to standard enthalpies of formation, if you want to calculate a reaction energy from standard enthalpies of formation, two things. One, what you get is a comparison between the standard states of the products and the standard states of the reactants. But you have to know a standard enthalpy of formation for every chemical in your chemical reaction. The advantage of bond enthalpies is, with just a few bond enthalpies, you can calculate the reaction enthalpy for a myriad of chemical reactions. Many of the organic reactions you can get reaction enthalpy, but that's an estimate because these are averages. So we found that you could take the bonds broken minus the bonds formed, and you could get an enthalpy for the reaction, or you could use the summation, take the heats of formation of all the products, subtract away the heats of formation of all the reactants, and get reaction enthalpies that way. And this myriad of lines connecting all those things, go back through the slides. We could post an animation of the slides, maybe so you could go through that, but of course you can review the video as well. And I'm sure Melissa has that up there as a learning bite for you to page through. So today we'll continue that. How am I running this? Oh, I have to swipe today. Oh, why am I a board? I might have annotation. I think this is PowerPoint annotate that's happening. How does one turn off PowerPoint annotation? Stand by, guys. Oh, goodness. So we've tried yet another configuration of the board. I'm pretty sure this is not annotate. Yeah, that's even a different color. That's PowerPoint annotation. But I cannot close the presentation in this mode. How about that? Okay, that seemed to have closed PowerPoint altogether. Okay, that's fine. We'll restart PowerPoint. And I want to reopen this file, but I do not want to have it start in annotation mode. Let's just check the slideshow. Use presentation, start from the beginning. Current slide. It doesn't say that it's going to be in annotation mode. Oh, me oh my. Oh, there you go. Now those are coming up as the controls, as we expect. Sorry, guys. Technological issues here. We'll get back to where we were here, which was here. Okay, now I hope I can swipe. Yes. So we went through this chem quiz where we found that the bonds we were breaking here were bonds, the elements in their standard state. We were breaking carbon-carbon bonds, and those could be carbon-carbon bonds in the standard state, just a block of carbon, hydrogen-hydrogen bonds in H2, and oxygen-oxygen bonds in O2. So those looked like elements in their standard states. Then we said, what bonds do we form? Well, if we looked at the bonds formed and we just pieced them together, we found we could piece together an ethanol molecule. It had all those bonds in it. And so this was the enthalpy of formation of ethanol. And even though we could calculate it from bonds broken minus bonds formed, it would be an enthalpy of formation. It wouldn't be as accurate as the table. So you could go to the table and you could calculate, look up the enthalpy of formation of ethanol. If you did these calculations, break 4 carbons, break 3 hydrogens, break half a mole of oxygen double bonds, and make a carbon, make 5 carbon hydrogens, make a carbon oxygen, and make a oxygen hydrogen, subtracted those enthalpies away, you would get a number close to this. But if I use bond enthalpies, then that is an estimate. This is what we call the standard number. So that's the standard formation of ethanol, and we actually went and got that from the table. So we ended here. Which butane combustion will release the most heat? So I have a mole of butane, pardon me, a tenth of a mole of butane, and I have a 2/10 of a mole of butane. I have a tenth of a mole of butane in with a mole of tenth of a mole of oxygen in the same balloon. We're interested in which releases the most energy. And this is fun to do in the room because this releases a remarkable amount of energy as heat. So you're in Pimentel, which is 500 seat lecture hall, and you ignite these balloons, and people in the back row can feel the wave of heat hitting them. So a lot of strong bonds being formed is where that energy comes from. Not the breaking of the bonds, that requires energy. It's the strong bonds being formed in carbon dioxide and water that's driving that reaction. So think about that for a minute. I'll join a Zoom room and we'll see what you're thinking. Good morning, guys. Ooh, I have Okay, had a good discussion about that. Let's see what you're thinking. We'll go to Ryan's source, and she will tell us. A slow switch. The other screen switched so much faster. B and C are both popular. The B is more popular than the C, and this comes back to pretty exciting. A chem quiz we did the first day of class, except we did it with hydrogen instead of butane. And what you remembered was this last balloon with the oxygen already in it had a tremendous explosion. We could have showed it to you again with Lonnie, but this balloon explodes and there's a wall of heat. This balloon explodes and there's a wall of heat. This balloon explodes dramatically and there's a wall of heat. But which one gives off the most energy? Well, where's the energy coming from? It's coming from the formation. Can I go back to my thing here? Boy, why does Chrome also show? Oh, do you think I was running it in Chrome and that's why I was writing on top of it? Sorry, we're having a technology discussion. All of these balloons form water and carbon dioxide, and it's the formation of the OH bonds in water and the carbon oxygen bonds in carbon dioxide that are releasing that energy. They're coming together, and when they come together, the carbon and the oxygen form a very strong interaction. That's an exothermic process. You know that's an exothermic process. Why? Well, we've been talking about positive and negative things coming together and that going to low energy the whole semester. Well, another way to remember it is they come together. That has to be releasing energy because pulling them apart takes energy. You know, pulling them apart you got to pull things apart that are bonded. That has to take energy. That has to be endothermic. So coming together must be exothermic. And indeed it is. So which is the most exothermic? Which releases the most heat? Well, it's the one that forms the most bonds. Because the carbon dioxide and oxygen hydrogen bonds are the same for each of these. The products are the same. So what you want to form is as many as possible, release as much energy from as many bonds as possible. And the way to get the most bonds is to start with the most fuel. So even though this one is going to be dramatic, it's dramatic for a different reason. This one releases more energy. It's boring and it happens relatively slow. It explodes through the lecture hall, giant ball of fire. It's really cool. And then this one, kaboom, not as big a ball of fire, but a big bang, a concussion associated with it, releasing less energy when it does that. Why does it give that big combustion bang? Well, we're going to talk about that in another unit. The answer is this one can go faster. So the amount of concussion you get, the drama of the explosion, is often how fast the explosion goes. So because the oxygen is mixed in already, this one is primed to explode. This one here, you pop the balloon and oxygen has to rush in and mix, and then the reaction can occur. And that's a slow step, relatively. This one, it's already there, mixed. You ignite that baby and kaboom, it goes. And that pushes back the atmosphere very fast and you get a concussive, loud explosion. So if you're going to blow something up, it's nice to have a lot of energy. It's nice to have a lot of fuel in your bomb. I don't know why I'm talking about this. And this is broadcast worldwide. We wouldn't want to encourage any terrorist organizations to how to build better bombs, but a lot of energy is good. But if you can release it as fast as possible, you'll do more damage because that expansive concussion is what causes the damage. So there we go. Bond bond breaking and bomb making all in the same slide. Oxygen in excess. So all you need to do is get as many moles as possible. And this goes back to something we've said many times. Energy is an extensive property. The more stuff you have, the more energy you have. So yes, this one released more energy. It has more energy. There's more of it. Energy depends on the extent of the system, the number of molecules. All good lessons there. So that's our discussion of bond energy. Let's do just a fun one here. Here's a combustion reaction, and in this case, we're burning a biological molecule, either a sugar or a fat. They both have basically the same components: carbon, oxygen, and hydrogen. So this is just generic XYZ. What is their calories per gram? And calories per gram are an important thing that we think about. Calories per mole aren't very important for nutrition because how do you get a mole of sugar? Nobody wants to think about that. You want to think about if you eat a gram of sugar, what kind of calorie are you bringing in? Well, a gram of sugar contains about 4 calories, and these are nutritional calories. So it turns out a nutritional calorie, we have this calorie that we use, and I try to not use the term calorie at all. That's the old form of energy. We use joules, and a calorie is about 4 joules. But we use the term joules. That's the metric unit. It's the established scientific unit for energy, not calories. But even so, these are, when you put a capital C for nutritional calories, they're 1,000 times the calorie, the scientific calorie, that's 4 joules. So these are 4,000 joules in this in these foods. So 4,000 joules per gram. That makes it sound a lot more dramatic. So 4,000 joules per gram. Here, fat, much more dense in energy. So now we can talk about energy density. Sugar packs 4 calories for every gram. Fat packs 9 calories in the same mass. So you eat your avocado, you get a tremendous amount of energy from the fat. One thing's different though, the avocado, only about 15% of it is fat. The rest of it, most of the rest of it actually is indigestible fibers. So they're called, I think it's called dietary fiber or insoluble fiber. If you read the nutrition facts, insoluble fiber, that's a carbohydrate actually, but it can't be digested readily, so you don't get calories from it. So that's about 350 calories then, because it's 15% fat. You'd have to eat 7 of them a day to maintain a 2,000-ish calorie diet. And that 2,000 calorie diet is just a broad recommendation for about how many calories on average people bring in. Of course, that varies widely, huge standard deviation on that. 6 donuts a day would also do it. So depending on your preference, you could eat 6 donuts a day, and you burn energy at about 100 watts. And these are in units of joules per second. So you burn about 100 joules per second. So you could calculate, you could back calculate this. A watt is a joule per second. So this is 100 joules per second you're burning, and that's kind of what you call your basal metabolic rate. So when you're not doing anything too strenuous, you could be sitting, resting, it's a little lower than this, casual walking, concentrating on Chem 1, anything that takes a little more energy than just sleeping. So a basal metabolic rate of 100 joules, 100 watts. So at 100 joules per second, and you're bringing in from a gram of sugar 4,000 joules, it's going to take you how long to burn up those 4,000 joules at 100 joules per second? So it takes 40 seconds, but you take in a lot more sugar when you eat a donut. Take in 100 grams. So 100 times 40 seconds, 40,000 seconds. There's about 36,000 seconds in a day, right? So it takes you something like a day to burn off one donut just thinking about Chem 1. All the rest, unfortunately, gets turned into that and stored right there, as you can see on your instructor. So you do a chem quiz kind of based on that, which is the correct relationship for heat released per mole in the following reaction. So here we do have sugar, glucose, C12H6O6, reacting with oxygen. Here we have that iron, I keep saying aluminum oxide, iron oxide, aluminum, the thermite reaction. We need to go to the editor and just edit that segment out. I'll start again. Here we have, we're interested in how much heat is released per mole in these reactions. Here we have glucose, C6H12O6, forming carbon dioxide and water as it burns in oxygen. And here we have that thermite reaction where iron oxide reacts with aluminum to form iron metal and aluminum oxide. Which of those releases the most heat? So think about that for a minute. You had a chem quiz started. I think I can give you the group of 4. So you have some data to work with. And I think the best data to work with is down there. I'm just going to bring that into the room so we can all see it a little better and hop into a breakout room. Okay, let's see what you're thinking. We're back with the whole class. I had a good analysis in that breakout room. So I want to go back to, you're going to show us the result. And the result is, I don't know, one or the other, we're saying. Well, let's go and get my thinking on that. So you had to look at this reaction, and you had to look at the iron oxide reaction. Now, they produce different products. So you could do this, that calculation. So here is the standard enthalpies of formation of the products with the stoichiometric coefficients minus the standard enthalpy of formation of the reactants. And you'd get a number that we recognize. Oops. For the other one, so you get this that we recognize. Why don't I write the number down there? I do not, but you can see it's a big number that you can almost do in your head, right? Because that is 16,000 minus another 18,000. So something like 30,000, I mean, 100. So this is 2,000 or 24. Yeah, can't even do it. 2,400 minus 1,800. So that's around 3,200 minus a minus. So you're around 2,400 total for this, minus 2,400 total for this delta H. So just doing that roughly, this is around something like minus 2,400-ish. Am I off by a factor of, seems like I'm off by a factor of 2 there. 6 has come out in front. 400 times and 300 is 700. 6 times 7 is 7,200 minus 1,200. Why am I? Isn't it funny how you can't do the math on the spot in your head? I'm sticking with the number I got, something like 2,400. What is the other one? The other one, how did we go back in this?
Swipe backwards.
It does go back if I swipe back? Okay, I'm going to swipe back and look at that. Oh, I didn't have to. At the total reaction. So that's this one. This one we can get just by looking at the table, because that's the formation of iron oxide and the formation of aluminum oxide are both in there. So if you write the formation of iron oxide from the elements in its standard state, the formation of aluminum oxide from the elements in their standard state, one of them in that direction, the other in this direction, you could subtract those two numbers to get that, the enthalpy of that reaction. And that obviously the enthalpy of that reaction is going to be the difference between those two numbers. So something like 800 kilojoules per mole. So your gram of sugar burning is much higher release of energy. Oh, I did do that. Thank God I did do the calculation. So my 2,400 was pretty close to around the 3,000 kilojoules per mole that releases. So burning that mole of sugar, way more energy released than the burning of that thermite. So you saw thermite, and thermite melted iron. So this one, you get molten iron, but eating a gram of sugar, your body is taking in, or a mole of sugar, and a mole of sugar is around 180 grams. That's the molar mass of sugar. So eating 200 grams of sugar gives your body the energy to melt a mole of iron. In fact, many times over moles of iron. That's amazing. I think we have Lonnie doing that. So we've already seen him do thermite. Let's see if we can see Lonnie actually, whoops. Oh, Lord. Let me just see if I can. Oh, goodness. Go big. Okay, so here's Lonnie. He's got a donut here. He's going to take just a little piece of the donut, and he's going to do the combustion reaction. But of course, just burning it with a torch is boring because the density of oxygen is low. He's going to put it in liquid oxygen to get the reaction to go. So here's a donut. He's going to start the combustion with the torch and then continue the combustion in liquid oxygen. And then the reaction will go very fast and release all that energy from just that slice of donut. And that's certainly a sixth or less of that donut. So there's the combustion starting slowly. It's now burning. So the combustion is happening. Now let's go do it fast in oxygen. You can see it already going much faster because of the density of oxygen, and then in the liquid oxygen. So this is, you can see now 100 watts, 100 joules per second coming out of there. That's the intensity that you can burn at. And this is much more than 100 watts. Just that tiny slice of donut. That's a lot. And I think it flew out in the end. So just a tremendous amount of energy in sugars. And that's why they're so effective at driving us high energy density. And it's also, one of the reasons we have to limit our intake in sugar because it does have so much energy. We'll end up just storing it as fat if we take too much in. So let's continue then through this to our next topic. Here's burning of acetylene. That we already went through. Maybe we didn't do it. You could go through that one. Here's burning. Here's burning. Here's eating your donut, your 400 calorie donut, and trying to drive a light bulb. So if you have a 100-watt light bulb, how long can you drive the 100-watt light bulb after just eating a 400 calorie donut? So 1600 times 10 to the third joules. 400 calories, multiply that by 4 to get joules. That's 1600, and that's a kilocalorie. So multiply that by kilo. So 1600 times 10 to the third joules. That's a tremendous amount of energy. How long does it take to burn that? We did this in our head a second ago. That is something like one donut takes 4 hours to burn off when you're burning at 100 watts. Okay, so let's go on to our next topic here, and we've come pretty far here. We know a lot now about the structure of molecules. We understand energetics in a very sophisticated way. We understand transfer of energy from one system to another. We understand where energy is stored in systems. Energy is stored in bonds, in potential energy. It's stored in the kinetic energy, the motion of particles in systems. So we understand the energy landscape of the universe so far. There's a few more things to add because we haven't talked about where the energy goes, how we predict where the energy would go. So how do you predict where the energy would go? That's the subject of the second law. of thermodynamics. So let's see if we can look at the second law of thermodynamics. So see if we can go to Echem here and show that. So here, I don't know how this will run. We haven't practiced this before. It's going to go to an Echem demo. So let's just show that. So here in this demo, this is me again. And that's funny. I'm wearing the same suit I was last demo we showed me doing this. So I'm going to take two salts, and I got a thermometer. So this one is sodium hydroxide, and I'm going to put sodium hydroxide, water, let it dissolve, and look what happens to the temperature of that system. It drops considerably. So dropping in temperature as I mix that together. So if that temperature is dropping, that means that's an endothermic reaction. I'm pulling heat away from the system, which is mostly the water around it, pulling away from the water around it and causing the water to drop in temperature. Calcium chloride, do the same thing, mix that up, and look what happens here. That temperature goes flying up. So this is an exothermic reaction. So very exothermic reaction. So what is going on? I ask what is going on. You say, well, I'll tell you what's going on. Those salts are dissolving in a liquid. But for the first salt, let's get rid of my face to talk about that. Let's go to back to the PowerPoint, or let's just go to a straight whiteboard. So for the first one, let's get this thing. Let's get this thing out of I'm annotate on top of whiteboard. That's like double annotate. So what we had is we had the sodium hydroxide, and black screen is better as we recall. We had sodium hydroxide dissolving in water to form the Na plus and the OH minus ions, and that cooled off. So that means NaOH is in a sense higher energy than the Na plus OH minus ions. It dropped in energy. It gave that energy out to the surroundings. Surroundings was mostly the water. So the system was these was the sodium and hydroxide ions. The surroundings was the water. Is that the exothermic one? That was the first one. I'm sorry, the first one, the temperature dropped. Yes, I'm sorry. First one, the temperature dropped. So if the temperature dropped, that must mean going from sodium hydroxide to these guys. I have to turn them over completely. This reaction was endothermic. The reaction, the system got cold. So what I had was the NaOH solid. To get that into the Na plus ions and the OH minus ions, I had to absorb heat. And when I absorbed heat, that came from the surroundings and cooled off the water. Okay, so heat comes in from the H2O to make that go up. The H2O, the surroundings, its temperature goes down. For the other one, it was calcium chloride, I believe. And that breaking up into the calcium and the chlorine is the exothermic one. So calcium chloride, when it dissolves into the calcium plus ions and the Cl minus ions, that releases energy, and that energy goes out into the surroundings. which is mostly the water, and heats up the water. So we're at a fundamental conundrum here, and you might not realize that it's a fundamental conundrum. Why did these both go? I mean, why is this one that has to absorb energy go just as readily as this one that releases energy? We've always said to ourselves, everything wants to go to a lower energy state. That'd be great. But when I dissolve sodium hydroxide in water, it goes to a higher energy state. So what is the driving force? How do I tell just from looking at the energetics from doing this in a calorimeter? I can't predict from the energy that comes out or goes in whether the reaction will proceed or not. This one proceeds as endothermic. This one proceeds as exothermic. There's got to be something else going on that tells us why that happens. So, what is that other thing? That other thing is something we call entropy. And so how does that work? And this is counterintuitive to start with as well. So what is the natural direction of change? Both of those were the natural direction of change, but one was endothermic and one was exothermic. Should do that the other way. One was exothermic, released energy. One is endothermic, it absorbed energy. Why did both of them just go? Well, it has to do, in a sense, with the arrangement of the particles, the energy space available to the particles. And we can look at that from a simple statistical argument to start, and then we'll apply it to the chemical systems. So here I have a bunch of gas particles locked in one side of a system. I'm going to open this valve, and what's going to happen when I open that valve? I think you probably know that when I open the valve, those gas molecules will rush to the other side. They rush to the other side, but they do it under conditions. This is even a more strange thermodynamic experiment from what we've done, because now there's no energy change. This system has the same energy as all of them on one side. So there's no favored state energetically. No work and no heat flow. So if there's no favored state, how do we pick which state is going to exist? Which is the state that we will see? What is the real favored state if it doesn't have to do with energy alone? Energy alone, I can't choose the favored state. All the molecules on this side, or all the molecules on this side, or all the molecules on that side, energetically the same. But we know that when we look at this, and we did this experiment, would these switch back? The energies are the same. Shouldn't they just switch back between one and the other? Shouldn't we be able to look at the system and sometimes see it in this state as opposed to that state? They're energetically equal. And the answer is no. There's a direction to the universe. There's a time arrow to the universe, and it's a statistical time arrow. We'll talk about that more as we go. So let's look at this from a purely statistical argument. Let's say there were just two particles trapped on this side. There were two particles trapped on this side, and I opened it. The result would be one particle on each side. And when it's only two particles, there'd probably be times when both of them are on one side. For sure, there's only two of them. But one particle on each side, so I'm doing the sides of the flask now, one side of the flask, the other side of the flask. What if I have three particles? well, then there's still the probability of having 1 on one side and 2 on the other. Or there's the probability of having them both on the same side. But there's different ways to arrange those. So let's look at that. So with 3 particles, I could have the arrangement of both of them on one side, or both of them on the other side. That corresponds to this and this. And there's one way to arrange that. Both of them on the one side, there's only one combination of that. But what about 1 on each side? Well, 1 on each side, there's 2 ways to achieve that. You could have this guy on one side and this guy on the other side, or they could be switched. You could have this guy on this side and that guy on the other side. 2 ways to do that. So that's what this represents. 1 way to do both on one side, 2 ways to do 1 on each side, and this is just the other 1 way to do them on the other side. So let's continue that analysis. Relatively simple. We'll go from 3 to 4 particles. So now I have 4 particles, and the same thing. There's 1 way to have all 4 of them on one side. There's 4 ways to have 1 on one side and 3 on the other. And that should be obvious. It could be any one of the 4 on one side and the other 3 on the other side. 4 ways to do it. Any of the 4 could be over here. There's 6 ways to do the 2 particles on one side and 2 particles on the other side. How am I making this? I'm making this little triangle here in a very simple way. I write 1 here, and then I add the numbers. So I add 1 and 1, and I get 2. And then here I add 1 and 2, and I get 3. I add 2 and 1, and I get 3, and then 1 here. To form this next row, 3 and 1, put my 1, 3 and 1 to get 4, 3 and 3 to get 6, 3 and 1 to get 4, and 1. So it's a simple process of generating this triangle. I'm going to do it for 6 particles. By the time I get to 6 particles, this guy here in the middle is what I am interested in. I seem to have stuck back on. I'm doing both writing. Oh, maybe it's because I have the pen. I can write and I can swipe. I don't know. This writing is happening in PowerPoint. You guys don't care about the technology. But so now the combination where there's 3 on one side and 3 on the other, there's 20 ways to do that. And there's still only 1 way to do all 20 or all 6 on one side. So now there's 20 ways to do equal on each side and only 1 way to do all on one side. So if you look over at that thing with those particles moving around and you look once per second, 20 times you'd see them distributed equally across, and 1 time out of your 20 you'd look and see them all on one side. We can continue this. This number in the middle, which what we want to know about, gets big really fast. By the time I'm just to 50 particles, it's hundreds of billions of times more likely that you'll have them spread out equally than way out here where you'd have them all on one side. So you have to look at that 100 billion times, and you might find one of them where they're all on one side. So it's simply a statistical argument that says if these guys are moving around freely and they can access everything, shifting around back and forth, then when the number of particles get large, you just don't see. It's just indistinct. It's just so rare that they'd all be over to the other side. And that's not energetic. all of them on this side is the same energy spread out as all of them on the same that side. Nothing, no energetics to do with that. It's simply the statistics of these moving particles moving from side to side randomly. And of course, when we get to real numbers of particles, that's only 50. Imagine when you get to a gas, a mole of particles. Now this number in the middle is 10 as 2 to the 10 to the 23rd. That number is already much bigger than all the particles in the universe by far. So there's virtually zero chance you're ever going to see the particles over on one side, even though it's energetically the same. There's just too many ways to do them spread out over the other configurations. So what we have is a lot of states available to the system. We have what we call microstates, and the microstates are what we've gone through. The microstates for the 4 particles were, well, one of the microstates is all of them on one side. Another microstate is 1 on one side and 3 on the other. Another microstate is 3 on each side. Each of those have exactly the same energy. None is favored energetically, but they're just moving back and forth really fast. So that is the one you see most often. And that one you see most often gets ginormously large. That's what we call statistical inevitability. It's, you have to say that like, what's the guy's name in Matrix? Yeah, Neo is the hero. What's the horrible guy who's, he goes, the guy, you've seen the Matrix? The Matrix, the evil Matrix guy is chasing Neo, and whenever he catches up to him, he says stuff like, it's Agent Smith, yeah. Mr. Anderson, it's statistically inevitable that you will survive. It's statistically inevitable that you will see this situation. So that's kind of interesting. There's a demo to see this, but I didn't change the names of these guys. Where is my demo? Stand by. That is here and here and here. Come on. I'm going to open it on this other machine here. And we'll just switch sources. So this is a probability thing. And as a probability thing, it relates exactly to probabilities and gaming. Exactly the same. So let's look at Plinko, the game. So here's Plinko the game, and let's get to a 6-row Plinko board. There's a 6-row Plinko board, and if you let the balls fall through the Plinko board, where are they most likely to end up? Well, they're most likely to end up in this center bin. So you have 6 bins, and the bins correspond to the fact that you'd have 1 particle on one side. This is the bin where you have 2 particles on one side. This is the bin where you have 3 on each. Did I do 6? 2 on each side. 1 on one side, 2 on one side, 4 on the other side. 3 on one side, 3 on the other side. 1, 6. This is 3 on one side, 3 on the other side. This is 2, 1, 1. Why can't I do this? 1 on one side, 6 on the other. 2 on one side, 4 on the other. 3 on one side, 3 on the other. 2 on one side, 4 on the other. 1 on one side. 1. I have 7. 1, 2, 3, 4, 5, 6, 7. I have 7 bins. Why do I have 7 bins? Oh, I have 6 rows of plinkos. 1, 2, 3, 4, 5, 6. One, 2, 3, 4, 5, 6. 6 rows across. So the probability of finding it in the center is the highest. Let's go to probabilities. So we don't have to look at the balls here. Stand by. Stop that. Look at paths and go. So why do they tend to end up here? Why is this the most probable spot? The most probable spot is where it's most likely to go. There's all these possible paths, and they're all essentially equal bounces off everything. So, but there's one way to bounce all the way down and get here. There's many ways to bounce in the middle and get here. There's only one way to bounce all the way down the side and get there. So these represent the number of ways you can get to each one of these situations. If you have more ways to be able to get to this situation, more probable courses to get there, that's where you're going to end up predominantly. You can go to more rows here. And as you go to more rows, the center becomes even more likely, and the outsides get less likely. And that's what we see. Probabilistically, these things, if you look at the system, are going to be the ones that fill over the outside ones. So simply because it's a more likely configuration, a more likely path, you get this kind of configuration. So it's just the likelihood, the statistical, hundreds of ways to do that, one way to do that. It's very rare you're going to see the gas with one particle on one side and all the rest on the other side. You're going to see it mostly with the particles all in distributed equally. And equally is relative. Sure, they're always moving. So at a snapshot, you might find a half plus 1% on one side, half plus 1% on the other side. But you're never going to see this state, them all on one side. So that's just a probabilistic, easy explanation of that process. It's a natural process. It behaves with following simple statistics. And you're going to find that everything in science behaves statistically. We've already seen it. We've seen these distributions of the motions of particles. They have different energies they can assume. Some energies are more probable than others, so they have higher populations. But that doesn't mean there's a distribution of them. And you guys that are going into biology, you'll be very interested to know that that's how biological systems work. If you have a colony of bacteria, the statistically possible thing The most likely thing to happen is the thing that happens. You can predict what's going to happen in your petri dish. There's so many bacteria doing the same thing that the statistical result will be the one you see. So a very important concept here. So we call this, we define from this something called entropy. We give it the symbol S, and it's related to this parameter W. W is the number of ways to arrange each state. So the entropy of this state, there are 6 ways to arrange that, is a higher entropy than this state where there's only 1 way to arrange it. And if you looked at the entropy of all the states together, you could do the probability of saying that's a less probable state. So entropy is defined as Boltzmann's constant, that 10 to the minus 32 constant, times the natural log of the number of states. Okay? This is the statistical interpretation of this thing called entropy. And this thing called entropy explains this. We had no energetic way to explain that. But we have an entropic way, a statistical way to explain that. There's nothing energetically happening here. This is just the most likely configuration, and that's why we see it. When you take natural log of W, and W are these ginormous numbers, then S is huge, and high S is good. High entropy is where systems end up. And high entropy is not where systems end up because of order or disorder. That has nothing to do with it. Remember, first day of class, we took a deck of cards. How are we doing? Let's do the demonstration. I'll get a deck of cards. Stand by 1 second. Interlude, you sing or something. I'm going to go. I'm going to be right back. I'm going to get a deck of cards so we can actually do the demo. They're right outside. Nice thing about working at home, can go right to the cabinet and get a deck of cards. We did this the first day of class. We said, and you guys hated it. You all got it wrong. Because we said, here's one state of this deck of cards. And that definitely corresponds to this state. They're all on one side. And then I said to you, what's the entropy difference between this state and that state? And the answer is 0. Why is that? Well, there was one way to do this state, all packed up over here. But there's only one way to do that state on the ground. The reason this is a big number is this is a combination of all the ways it can be on the ground. This is a combination of all the ways it can be on the ground. The particles have to be moving around and exchanging systems or entropy doesn't even exist. So that was one state. That is one state. I'll tell you there's billions of more states like that. But if we're only talking about that one, then natural log of 1 is 0. That has entropy 0. This state, there was only one way to do that. Natural log of 1 is 0. Those two states have the same entropy. If the cards were moving around the room randomly, then the state here and all of those states would have a high entropy because we're occupying them all. We're occupying every possible state. If we're occupying every possible state, then we'll most likely be in the highest, most likely state. Then there's an entropy difference. No motion, no entropy. If you'd like, go back and explain that to your, if you got the wrong explanation in high school or anywhere, just go back and say, that is not exactly right. The deck of cards fall on the ground. That's one of the microstates. This is another microstate. And if you talk about single microstates, W1, then that entropy is 0. Cool. So we're going to define this. Oops, a little bit of a typo there. We're going to find this thing called entropy, and we're going to look at entropy changes. We're going to look at entropy changes between the system and the surroundings. And it turns out the entropy of the universe, the sum of the entropy changes in the system and the surroundings, is always greater than or equal to 0. My 0 showed up over here. Oh, I think the way this PowerPoint is going, I can just write with my finger. Oh, now I can't. Oh, but if I'm holding the pen, I think it's the pen close to the board. No. Yes. So that is always greater than 0. So entropy of the universe for any process is always greater than or equal to 0. So that tells us the direction of things. Entropy is the time arrow of the universe. Things go to an increase in entropy of the universe. Any process that proceeds with an increasing entropy of the universe is the favored direction. So now we didn't have any direction here energetically. We add a statistical argument and we have a direction. And as you know, a couple of people have mentioned the expansion of the universe. That's going to an increased entropy state continuously. The entropy of the universe is always increasing, mainly because the volume of the universe is always increasing. And if you go to volume, higher volume, there's always more ways to arrange something in a bigger volume than a smaller volume. So the entropy of the universe is being dragged to higher entropy by the expansion of the universe. So that's always true. You can talk about spontaneous processes. Those are the processes where these are the processes that go. We call them spontaneous. So if it's entropically favored, the universe favors it, that's called spontaneous. And that's kind of a funny word. People get, it's not spontaneous in the sense of, ooh, let's have a party out of the blue. It's spontaneous in the fact that that's the natural direction of the universe. If you have a process fixed and you release your constraints, it will spontaneously go in the direction of higher entropy for the universe. So spontaneous processes, entropy of the universe, always greater than 0. If you have 0, there is the 0 case. The 0 case is where the universe is indifferent to your products or reactants or your two states. Completely indifferent between the two states, then the entropy of the universe is 0, and those processes are what we call reversible, also a term that gives people consternation, and this irreversible. But we can also just use equilibrium. So states where it doesn't matter, the entropy of the universe is the same, whether you're in this state or in this state, that means truly, the universe doesn't care, you can be in either state. And then, of course, having entropies decrease in the universe cannot happen. That is a profound bit of stuff here. I'm going to page through these. Those are our demos. Let's ask a question. 6 distinguishable objects. There they are, balls, in 2 boxes. How many ways can you have 4 in the left box? Think about that for a second. We'll start a chem quiz. I'll jump into a Okay, let's come back together and see what you're thinking about that. Ryan can show us the distribution. And 15, overwhelmingly popular. I agree with the 15s. Why is that? Well, in general, the number of things, what you're doing is you're choosing R things from a group of N things is what you're doing. And there's a mathematical relationship to do that. You can look up your combinatorial mathematics. We don't necessarily have to do that because we also have this Pascal's triangle thing. And we can say, well, I'm at the 6 particle stage. And if I want 4 in one side and 2 in the other, here's, this is the probability of having them all on one side. Here's the probability of having them 1 on one side and 5 on the other. 6 ways to do that. Here's the probability of having 2 on one side and 4 on the other. So there's 15 ways. There's 1 way to do all 6 on one side. There's 6 ways to do 1 on one side, 5 on the other. There's 15 ways to do 2 on one side and 4 on the other. There's 20 ways to do 3 on one side and 3 on the other. That's what I was trying to write down on the Plinko board, but I was just messing it up altogether. I have to retape that entire sequence. Or, of course, you could say, okay, that is the number of ways, 15 ways to put 4 on one side and 2 on the other. I've made them indistinguishable now because they'd be indistinguishable in nature, but we know there's 15 ways to do that. And we can look at the 15 ways. If you could drop us down here, the camera down. It's a little bit of a mess here all of a sudden. So I have here in front of you, give me a little zoom. I have here in front of me a table, and I have on the table dog treats. And I have 6 distinguishable dog treats. 1, 2, 3, 4, 5, and 6. Is that distinguishable from that one? No. 6. There are my 6 distinguishable dog treats. If I had them all on one side, there's 1 way to do that. If I take 1 to the other side, there's 6 ways to do that because it could be any one of the 6 over there. Whether I can distinguish them or not, I have them distinguishable so we can tell which ones we're doing, but there's still 6 combinations of that. How about 2 on that side? We're saying there's 15 ways. Can you look critically at the shot? Just zoom in just a little more if you can. So there's 15 ways to do this. 2 on one side and 4 on the other. And you could count through the 15 ways. It could be that pair over there. That's 1. That pair over there. That's 2. That pair over there. That's 3. And now there's different pairs. So I can break this guy up, use that pair, 4, that pair, 5, that pair, 6, that pair, 7, that pair, 8, that pair, 9, that pair, 10, that pair, 11, that pair, 12, that pair, 13, and there's 2 more pairs that I missed. I should have left them closer together. I missed 2 of the pairs in there. But that's the origin of this saying take 2 things from 6 things. Take pairs from 6 things. What are the total number of pairs? And if you have the total number of pairs in another box, then that's the distribution between the two boxes. So give me a camera up. And you're going to expand. So this idea here of taking the pairs of things is here. R is taking 2 things from your 6 things. So R is 2, N is 6. And if you put that in there, R things, true N minus R, I need to throw it in here. Choose 2 things from 6 things. N is 6. R is 2. So N minus R is there. Oh, this is 4 things from a set of 6 things. Doesn't matter. You can either, that's symmetric, right? You can choose 4 things from 6, or you can choose 2 things from 6. That's just this side or this side. So I chose 4 here. So choose R 4 things from 6 things. So N is 6, R is 4. You can do that mathematics if you know how to use your factorials, and you get, am I writing on your screen? We're stuck in PowerPoint Annotate. I'll bring the pen with me. I was able to, hold this end of the pen near it. Hold this end of the pen near it. I don't understand exactly how I switch back and forth. It's handy to switch back and forth between PowerPoint and Annotate. I haven't figured it out yet, though. So let's do, I'll just talk this one through with you. I have a process here. I start with 4 balls on one side. I go to 1 ball moving over, and then 2 balls moving over. That's our free expansion. That's the first 3 steps in the free expansion of gas. Start all on one side, and you start distributing to the other side. Which step, if I do it stepwise, has the greatest increase in entropy, the greatest delta S for those steps? And delta S I can calculate from ln of the final state minus kln of W for the final state. So natural log of W for the final state times K, natural log of W for the initial side, times Boltzmann's constant, where W is the number of ways to arrange those states. So I can do that. Of course, I can rearrange this. This is a property of logarithms. If you take a difference in logarithms, that's equal to the logarithm of the quotient. So you should know those kind of logarithmic rules. They're very helpful. So this, the difference between the 2 logarithms, is the same as the logarithm of the quotient. So how does that work? Stepwise entropy change. So let's go from state 1 to state 2. There's one way, the final, the initial state, to do that. There's 4 ways to do this next state. Any one of the balls could be over there. So that is, delta S is ln K of 4, or K ln of 4. What about this state? So here I have this state. Of course, we know there's 4 ways to do that, minus this state, the final way to do that. And we know there's 6 ways to do that. So there's that entropy. And then we're interested in the 1 and the 3 states. But here I've gone 3 to 1, not 1 to 3. So I'm going up. And now the final state is the 1 way, and the initial state is the 6 ways. So that has a large magnitude of natural log. That's the smallest number because I've got the final and initial state arranged there. If it were going from 1 to 3, then 3, the 6 ways would be the initial state, and 6 would be on the top, and 1 would be on the bottom. So that would be a high change in entropy. This, the fraction, if you take the natural log of a fraction, you get a negative sign coming out in front. So this delta S here, this delta S here is less than 0. These are all greater than 0. Oops, but I wrote less than anyway. These delta S's are all less than, delta S less than 0. No, these are all greater than 0. Goodness gracious, Mark. These are all positive because that's the natural log of a positive number, or a number greater than 1. Fractions, numbers less than 1, have negative natural logs. Numbers greater than 1 have positive natural logs. So these are entropy increases, and this first step, 2 to 1, has the natural log of 4. This has the natural log of 1.5. So the first step in the expansion is the biggest entropy change, and then the entropy change drops off as you go. Giant entropy change, and then drops off as you go. That's a really cool fundamental thing to look at in the future. We don't have time in this class to get into that, but the entropic stepwise entropics of expansion or processes in general is a very fascinating thing to look at. We can do this thermodynamically. So far, we've just gone all statistically. But there's a relationship between the statistical, and by statistical, I mean we were counting the number of ways something could happen. So statistical was S equals, I'm going to get myself into trouble here. I'll put it over here. Statistical was S is K, the Boltzmann constant, times natural log of the number of ways to arrange the system. That doesn't have any energetics in it. No heat, no energy, no nothing. But there are ways to relate delta S to thermodynamic parameters. And that's good because, as you've probably already realized, counting the ways is hard. If you got a mole of gas, you can't count those ways to arrange the system. So what is that? Well, we know there's directions of change that we recognize. If you drop a ball, the ball will drop and it will bounce lower every time. The natural direction of this is for the ball to come to a stop. And there's an entropic factor in there. What you're doing is you're causing heat absorbed by the ball gets hotter and the floor gets hotter, and those more motion in those particles in the floor and the ball are higher entropy states. So entropy is increasing as you do this. So this agrees with the natural direction of the universe, and it's related to heat, which is good. This, a ball just sitting there and having suddenly all the particles go in the same direction and lift the ball up, that never happens. That's the same thing as having all the particles spread out between two sides and then suddenly all of them rushing into one side. That would send the ball flying, but no one has ever observed a ball flying spontaneously off the ground. So that never happens. This, where entropy increases in steps and the heat lost in each of those steps, we know that causes the ball to slow down. That saps the energy of the ball, but it's an entropic step, and we write that as a thermodynamic entropy. One more example, hot and cool things brought together, the heat always travels from the hot to the cool. You cannot make cool things transfer their heat to hot things. thermodynamically impossible because of the entropy barrier. That is taking a little particles on one side and shoving them into and making all the particles move to one side. That's colder to hotter, and you can't do that. You're going to go hotter, lots of particles, to less particles on the other side, hotter to cooler. This always happens. Once in a while in the paper, I'm going over the time here, so we'll stop, but I have office hours. Once in a while in the newspaper, or sometime you'll see somebody claim that they've found a way to do this, go from cooler to hotter. If you could, you would be the master of the universe, because you could get infinite energy. You could take energy from cold stuff, put it in hot stuff, and then you'd have hot stuff, and you could do work or use that to make energy. But it can't be done. So let me just go through quickly and just tell you this expression, and then we'll pick up here next time. We can take the heat and the heat that flows along a reversible path divided by the temperature, and that is the entropy change. That represents that statistical spreading out of the system in thermodynamic terms. And we need that link to thermodynamics because statistical entropy, counting every microstate, is hard. Okay, so we'll talk to you tomorrow. We'll get Avery in here she was in here to snarf up these dog treats. But it is office hours too. So if you have some questions, let's hear them.
So first question. So is the second law of thermodynamics just that entropy cannot decrease?
The question is the first law of thermodynamics that entropy cannot decrease? Entropy of the universe, be careful. Overall entropy can't decrease. The best way to remember the second law, or a better way that I kind of remember it, is for any spontaneous process, the entropy of the universe must increase. That's the only way we can tell things are going in one direction or the other. The time arrow of the universe is towards increasing entropy. Consider this: if you have a deterministic system, so if I have a ball moving through space, let's just get rid of that thing if I can. Select it, erase it. Select, erase, erase this. I'm having trouble erasing this object, but I won't waste your time trying to figure out how to erase this giant object. I just thought it was easier to do than that, to learn the whiteboard. If I take it and I select it, get a trash can, erase. Or just click on the trash can itself. Double click it. Wait, go to select, double click it, click it once, erase. Got it. Whew. What was I talking about? Oh, time direction of the universe. So the question is, what's a good statement of the second law of thermodynamics? One statement is entropy cannot decrease for the universe. The statement I like to say is kind of the reverse. For any process that happens in the universe, entropy increases. So if you have a deterministic system, and that is a system for which I know all the forces. So there's a ball moving through space with momentum mv. Now that can move through space as long as I know that momentum m times v and all the forces in the system. Say there's a force of gravity somewhere. If I know all the forces of that system, I can tell you where that system will be any time t later. So that is deterministic. I can do that. But all these laws, all these forces of nature have this property that you could reverse them, and the process would go just as well in the other direction. So if I had a snapshot of the ball, I wouldn't know when I start the film whether it was going to go that way or that way because of this possibility. The momentum could be pointing that way, or the momentum could be pointing that way. The laws of physics are completely reversible. They work in both directions equally well. But that sucks for us, and to a certain extent, is if they work in the direction equally well, how come sometimes they go in this direction? They go in that direction only in time. That is, I run time in this direction, it goes in that direction. I can reverse time and run in that direction, and it'll go in that direction. Which one of these time directions is the one I want? That's what entropy tells you. Entropy tells you I'm going to go in the direction where the entropy of the universe increases. This direction, by definition, the entropy change in the universe will decrease. So this entropy thing is what separates the symmetric properties of motion, the time reversible properties of motion, and tells you which way things are going to go. Okay, other questions?
Can you explain the bouncing ball example of thermodynamic entropy again?
So the bouncing ball, yeah, we kind of rushed through the bouncing ball because we were getting near the end. But we had a surface, and we had a ball come down and hit here. And we know intuitively that if that ball bounces, its eventual state is rest. That's the time direction of the universe. We never see the ball fly up from the position and go to one of these states. So I have a natural direction of the universe I can observe. And I say, well, I know that's a natural direction I can observe. Can I attach some thermodynamic property to that? And the thermodynamic property I wanted to attach to it was these molecules in the ground being heated up, and these molecules in the ball being heated up, and those sapping the energy. This has some kinetic energy. It goes down here and transfers that into this useless form of energy, this heat. So I got some energy here, potential energy. I transfer it to heat. I don't have as much energy now. As I go up, I don't bounce as high. I get the heat. I do this, start my particles going every which way, more particles going every which way. I sap the energy, and that correlates with what we know happens, the natural direction of the universe. So all this heat being dissipated somehow correlates to the entropy of the universe increasing, because we know that's a spontaneous direction of the universe. And we know that this process, where all the particles in the floor suddenly move in the same direction and send the ball flying, does not happen in the universe. So we have an idea of that's statistically incredibly unlikely, doesn't happen in the universe. This is statistically very likely. And we say that that energy loss, that natural direction of the universe, is somehow caught in the fact that heat is being dissipated. So we haven't made a precise connection between the two, but we have this feeling, we have this inkling that these two things are related. And then we did say they actually are related. I'm not going to go through and derive any of that, but the reversible heat transfer divided by the temperature at which that heat transfer occurs is the change in entropy of the system. Okay? And the surroundings. I mean, we'll look at heat flows from the system to the surroundings. So it's the heat flowing out to the surroundings at their temperature is their entropy. The heat flowing into the system at its temperature is its entropy change. Anything else?
Wait, see if people are taking them. Why is it called reversible?
That's a good question. Why is it called reversible? Oh, this isn't touchscreen. I'm going to try something. Melissa, can Melissa hear me? Melissa, I'm going to put a Zoom room. Give me a Zoom room, and I'm going to put it on the big screen. Pick anyone. Join it. How do I go to full screen on my Zoom? Seems like there should just be a button to do that. I'm just going to do something because I'm just interested in how it works. I'm just going to go and show our Zoom participants. Oh, that closed Zoom when I did that. What's that? Oh, wait, it didn't close it. It put it all the way over here. Can I grab it? It's way too big. I can't reduce the size of that application very easily. Anyway, I just wanted to know if I could talk to somebody directly on the screen. I'll figure out how to do that because it would be fun to just talk to the person that's asking the question. Like Melissa. Melissa, turn off your mic and say hi. Let's see if we can hear you. I have to turn the standby. Self-conscious about turning your video on. Can you hear me in the Zoom room? If you're not self-conscious about turning your video on, can we get a few faces up here on the big screen? And you see me facing behind. Hi, Olivia. Anybody here? Is Elpin here? Elpin watches from Turkey sometimes. He might be on the where I can't see him. I'm gonna try and get. There we go. Hi, Christine. There's a few more of you. Are they on the big screen if I do that?
Yeah, looks great.
Hold on. I'm gonna try and get a few more of you in here. Sweet. Cool. Great. There you are, guys. Now there's 10 microphones going. So if I have that mic off, I think I'm okay. So there you go. There was a question, and I'll answer it in a second. Is that Will behind you cooking breakfast, Melissa? If someone from this group wants to ask a question, that'd be great. Any question, make one up. We did have a question. What was the question before I started screwing around? Something about.
It was, what does reversible mean?
Okay, what does reversible mean? The question is, why is it called reversible? So it's called reversible for a kind of a simplistic reason. It's called reversible because if I start using the board, stand by, guys, here. I'm going to try to do a split screen. I thought I could do that. Maybe I can't. No, I can't do that easily. Okay, guys. Well, thank you for doing that experiment. We'll play around with that. I would like to capture some video someday of me talking to actual people in the lecture. So we'll do that. The question is, why is it called reversible? And it's called reversible for kind of a simple reason. This reaction you could call a spontaneous reaction. We're saying that goes in that direction, and it goes in that direction because we know the entropy of the universe increases when that happens. If the universe is indifferent, that is, the entropy of this side and the entropy of this side are the same, then it's equally likely to find the system on either side. So that means the system is reversible in the sense that if you're here, just a tiny push will get it to go there because it's just as likely to be here. And if you're here, just as likely to push it, it would go either way. So the idea of being in equilibrium, where any little perturbation will send you to the other side, entropically equal states, I can switch between them. And so if I go this way, no worries, man. I can come back that way. Went that way, no worries, reversible. I'll come back. So that's the idea of reversibility and equilibrium. Okay, fantastic. That went well. We'll work on the technology of having you guys on the board because I'd like to capture some video of that just for fun. But thanks for coming today. Maybe Thursday we'll have a Zoom room, stay after a little bit and practice. Take care. We'll see you tomorrow. Avery is here. If you want to see Avery, where is she? Oh, if let's point the camera down. If you guys do want to see Avery as you're leaving, Avery's here. Avery, I'm over here, sweetie. I have treats. You knew they were here. Are you a good girl? I'm going to put these over here so you can come into the frame. Can you point the camera down a little bit more? There's Avery. Okay, Avery, sit. Good girl. Avery, down. Good girl. Avery, release. Come. Good girl. Treat for Avery. We'll turn so Avery can see you. Avery, come here. Can you zoom out a lot but point down? Avery, sit. Stay there. Can you zoom out any more so you can see Avery? There's Avery. Would you like a treat, Avery? Down. Good girl, Avery. Good girl. Do you like your treats? Good girl, Avery. Sit. Stay. Avery, you see this? This is a treat. I'm going to put it right here. Oh, you're going to go down. I'm going to put it right there. Okay. Good girl. Avery, sit. Oh, your legs hurt. You're having trouble sitting? Come on, sit. It's okay. Oh, her legs hurt. She's getting a little old. Let's try this. Avery, you see that treat? Good girl. Now let's back up again, Avery. And sit. Good girl. You see this treat? Stay. Sit. Come on. You can sit up. Good girl. Sit. Stay. You see that treat? Good girl. Now, Avery, I want you to come and ignore that treat, okay? Avery, come. Leave it. Good girl. Take that treat. Do you remember that treat is there? Take it. Oh, you do. Remember it's there. You're such a good girl. I wish it was easier for her to sit. Avery is 13, so her back legs hurt. It's hard for her to go from sit to stay and to down like she used to. Down. Good girl. Good girl, Avery. Release. Okay, there's Avery eating up our demo and loving it. We'll see you guys tomorrow.